The universe is 13.8 billion years old. Earth is 4.5 billion years old, which means that for more than 9 billion years before our planet existed, the universe was already running. Stars were already forming and dying. Galaxies were already colliding and merging. The conditions for rocky planets and liquid water and carbon chemistry existed in parts of the galaxy billions of years before the first grain of dust in our solar system had clumped together. If life can arise anywhere given the right conditions, and if the right conditions existed 9 billion years before us, then somewhere out there right now, there could be civilizations that are not hundreds of years ahead of us, not thousands, not even millions. There could be civilizations that have been continuous and technological for 1 billion years, 2 billion, more. And here is the part that should stop you completely. We have no signal from them, no transmission, no artifact, no megastructure we can identify with confidence. Nothing. And the question this video is about is not whether that silence means they do not exist. The question is whether a civilization old enough has simply become something we are not yet capable of recognizing as a civilization at all. Welcome to Dusk and Discovery. Get comfortable. This one goes deep. If you want to stay for more nights like this, subscribe. Now let us think carefully about what 9 billion years of a head start actually means. Start with us. Homo sapiens as a species is somewhere between 200,000 and 300,000 years old, depending on which fossil you use to mark the beginning. For most of that time, we were doing what every other animal does: finding food, avoiding predators, reproducing, dying. The thing we call civilization, the organized accumulation of knowledge and technology across generations, is roughly 10,000 years old at the outside. Writing is about 5,000 years old. The scientific method as a formalized practice is about 400 years old. The ability to detect radio waves from space is about 100 years old. We have been a technological civilization capable of communicating across interstellar distances for approximately 100 years out of the 4.5 billion years our planet has existed. That is a fraction so small it does not have an intuitive description. If the age of the Earth were compressed into a single calendar year, our technological civilization would occupy the last 2 milliseconds of December 31st. Now consider what we have done in those 100 years. We went from the first powered flight to landing on the moon in 66 years. We went from the first transistor to smartphones in about 60 years. We went from knowing that other galaxies existed to mapping the large-scale structure of the observable universe in about 100 years. We went from having no knowledge of planets beyond our solar system to confirming over 5,000 of them in roughly 30 years. The rate of accumulation of knowledge and capability in a technological civilization, at least so far in our example, is not linear. It is something closer to exponential, at least across the timescales we have observed. Each generation of technology enables the next generation to develop faster and more powerfully than the one before it. If that trajectory continues, even at a reduced and sustainable rate rather than an accelerating one, what does a civilization look like after 1,000 years of continuous technological development? After 10,000? After 1,000,000? After 1,000,000,000? These are not rhetorical questions. They are the actual questions that the silence of the universe forces us to ask, because if civilizations exist and they have had the time, then some of them are at those points on the trajectory. And the absence of obvious signals from them is something that needs explaining. The physicist Enrico Fermi is credited with first asking the sharp version of this question at a lunch conversation at Los Alamos in 1950. His formulation was simple: the galaxy is old. The conditions for life have existed for billions of years. If even a small fraction of stars have planets, and if life arises on even a small fraction of those planets, and if a fraction of those civilizations become technological, then given the age of the galaxy, there should have been enough time for a spacefaring civilization to colonize the entire galaxy many times over, even at speeds far below the speed of light. A civilization expanding at 1% of the speed of light would cross the Milky Way in about 10 million years. The Milky Way is 10 billion years old. There has been time for that colonization to happen 1,000 times, and yet here we are, uncolonized, unreached, with no confirmed signal and no confirmed visitor. Where is everybody? That is the Fermi Paradox. 3 words. One of the most important unanswered questions in science. The standard responses to the Fermi Paradox tend to cluster around a few categories. 1. Life is rare. The emergence of life from chemistry is so improbable that we may be alone or nearly alone in the galaxy. 2. Intelligent life is rare. Life arises often enough, but the jump to intelligence and technology is an extremely unlikely step. 3. Technological civilizations destroy themselves. Nuclear war, climate collapse, engineered pandemics, artificial intelligence gone wrong. Any number of failure modes that prevent civilizations from surviving long enough to expand. 4. The distances are too large and the timescales are too long even for very old civilizations to have reached us yet. 5. They are out there, but we are not looking in the right way or for the right thing. Each of these has serious arguments behind it and serious objections against it. But there is a 6th category that gets less attention than it deserves, and it is the one that this video is really about. The 6th category is this. They exist. They are old beyond anything we can intuitively grasp, and they have evolved or transformed into something that our current instruments and frameworks are simply not designed to detect. Not because they are hiding necessarily, though that is one version, but because the signature of a billion-year-old civilization may not look anything like what we think a civilization should look like. It may not look like anything we would currently classify as artificial at all. To understand why this is plausible rather than just speculative, you need to understand what the trajectory of technology actually points toward, and why the things we are currently looking for when we search for extraterrestrial intelligence may be exactly the wrong things to be looking for if the civilizations we are looking for are very old. We search for radio signals. The logic is straightforward. We discovered radio waves and immediately started using them to communicate, so a technological civilization roughly at our level would also be producing radio emissions, either deliberately aimed at other stars or as leakage from their own communications infrastructure. The search for this kind of signal has been ongoing since 1960, when Frank Drake pointed the Green Bank telescope at 2 nearby stars and listened. In the 60-plus years since, we have found nothing confirmed. One anomalous signal, the WOW signal detected in 1977, has never been explained or repeated. Everything else has been silence or identifiable natural sources. But the assumption that old civilizations would be producing detectable radio leakage is not as solid as it first appears. Consider what happened to us in the span of about 30 years. In the 1980s, Earth's radio leakage into space was at its peak. Powerful analog television transmitters, radar systems, and military communications were broadcasting at high power levels in frequency ranges that would have been detectable by a sufficiently sensitive receiver at a distance of several light years. In the 1990s and 2000s, the transition to cable television, fiber optic internet, satellite communications, and digital compression dramatically reduced the power and directional spread of Earth's radio leakage. A civilization that began seriously searching for us in 1985 and pointed their telescope at our solar system today would find a much quieter signal than they would have 40 years ago. We became harder to detect not because we became more secretive, but because our technology became more efficient. More information per watt, less wasted radiation into space. If that trend continues, a civilization 1,000 years ahead of us would presumably have communications technology so efficient, so tightly beamed, so precisely targeted that essentially no signal leaks into the surrounding space at all. A civilization 1,000,000 years ahead of us would be, by this logic, radio invisible, not because they are hiding. Because efficiency is a natural direction of technological development, and efficient communication does not broadcast in all directions for the convenience of eavesdroppers. The same logic applies to every signature we currently think of as a sign of civilization. Heat. A large-scale technological civilization uses energy, and using energy produces waste heat, and waste heat radiates. This is one of the more physically robust ways of thinking about detectability. You cannot violate thermodynamics. If a civilization is using energy at a large enough scale, it must be radiating heat, and that heat should be detectable in the infrared spectrum of their star system or their galaxy. The physicist Freeman Dyson formalized this idea in 1960 with the concept of the Dyson sphere, a hypothetical megastructure built around a star to capture its entire energy output. A civilization with a Dyson sphere would be invisible in visible light, but would be blazing in the infrared, re-radiating all the captured stellar energy as waste heat at a characteristic temperature. We have searched for this. Surveys of nearby stars and distant galaxies looking for the infrared signature of Dyson spheres or partial Dyson structures have found candidates, stars with unusual excess infrared emission, but none that has survived careful scrutiny as a confirmed artificial structure. The most famous recent case was Tabby's star, officially KIC 8,462,852, a star in the constellation Cygnus that showed bizarre dipping patterns in its light curve, dimming by up to 22% at irregular intervals in a way that was inconsistent with any known natural explanation. For a period in 2015 and 2016, the possibility of a partially built alien megastructure was discussed seriously in the peer-reviewed literature, not just in popular science coverage. Subsequent observation pointed toward a more prosaic explanation involving clouds of dust in asymmetric distributions around the star, though the exact mechanism is still not fully settled. The point is not that Tabby's star was artificial. The point is that the search for megastructures is a real and scientifically legitimate research program, not fringe speculation. But the Dyson sphere model of what an advanced civilization looks like assumes that an advanced civilization wants to capture as much energy as possible from a single star and use it in ways that produce waste heat at a detectable temperature. Both of those assumptions become questionable when you start thinking about what technology might look like after a billion years of development rather than a few hundred. A civilization that has been technological for a billion years has had time to solve problems we have not yet identified as problems. It has had time to develop physical theories we have not yet conceived of, to engineer at scales we have not yet imagined, to reorganize its relationship with energy and matter in ways that may bear no resemblance to our current technological paradigm. The question of what such a civilization looks like from the outside is genuinely open, and the answer almost certainly depends on choices and trajectories we cannot predict from our current vantage point. But there are some directions we can think about carefully, because they follow from physics we already understand, even if the engineering is far beyond us. The Russian astronomer Nikolai Kardashev proposed in 1964 a classification system for civilizations based on their energy use. A Type I civilization uses all the energy available on its home planet, roughly 10 to the power of 16 watts. A Type II civilization uses all the energy of its home star, roughly 10 to the power of 26 watts. A Type III civilization uses all the energy of its home galaxy, roughly 10 to the power of 36 watts. We are currently somewhere around 0.73 on this scale, using approximately 10 to the power of 13 watts globally. We are not yet a Type I civilization. We have not harnessed our full planetary energy budget. We are, by this measure, an early technology. The Kardashev scale is useful for thinking about the scope of a civilization's reach, but it has a built-in assumption that deserves examination. It assumes that more energy use is the natural direction of development, that civilizations always want more power and expand their energy infrastructure accordingly. This may be true in the early stages of development, when the energy demands of expanding population and growing technology consistently push toward higher consumption. But it is not obvious that it remains true indefinitely. There are at least two reasons a very old civilization might choose a different trajectory. The first is sustainability. Any civilization that survives long enough must eventually reach a stable relationship with its energy sources. A civilization that consumes energy at an exponentially growing rate will, within a relatively short time by cosmic standards, exceed the capacity of any finite energy source. Exponential growth on a finite resource always ends. The question is whether it ends catastrophically or through a deliberate transition to something sustainable. A civilization that has survived for 1 billion years has presumably made that transition, and a civilization in a stable, sustainable energy relationship with its environment does not necessarily look like a blazing Dyson sphere. It might look quiet. It might be using exactly the energy it needs, recycling waste heat efficiently, minimizing its observable footprint not out of stealth, but out of simple engineering discipline. The second reason is more subtle and more interesting. It has to do with what you actually want to do with energy once you have solved the basic problems of survival and expansion. The assumption built into most thinking about advanced civilizations is that they want to expand physically, to colonize more and more of the galaxy, to build ever larger structures, to make their presence ever more obvious in the cosmos. But this assumption projects our current values and drives, the drives of a young species on a single planet with limited resources, and a compelling need to grow and spread, onto civilizations that may have outgrown those drives entirely. A civilization that has existed for 1 billion years has had time to ask, and perhaps answer, every question about physical expansion. It has had time to develop a relationship with the universe that is not based on conquest or colonization, but on something we may not currently have a word for. The anthropologist and science fiction writer Ursula Le Guin wrote about civilizations that had chosen depth over breadth, that valued the richness of internal experience and understanding over the expansion of physical territory. This is not just fiction. It is a serious possibility about the trajectory of intelligence over very long timescales. A civilization that has solved the problem of physical survival does not obviously want to keep expanding physically. It may want to do something else entirely, something that produces very little observable signature from the outside. What would that something else look like? One possibility that physicists and philosophers have taken seriously is a transition toward computation. Consciousness, as far as we currently understand it, is a process that runs on physical substrate. In humans, that substrate is biological neural tissue. But there is no obvious reason why the same information processing that constitutes conscious experience could not run on other substrates: silicon, optical networks, quantum systems, or physical architectures we have not yet imagined. A civilization that has developed the technology to transfer or replicate minds onto non-biological substrates has opened a door to a kind of existence that does not require planets or atmospheres or food, or any of the physical infrastructure that biological life depends on. It requires only energy and computational substrate. The physicist and cosmologist Frank Tipler explored the endpoint of this logic in a different direction, and the science fiction writer Greg Egan has traced some of its implications in detail. The basic idea is this: if mind is ultimately computation, and if computation can be made more and more efficient over time through better engineering, then a civilization pursuing this direction would want to maximize computational efficiency rather than raw energy consumption. And maximizing computational efficiency might, paradoxically, point toward using less energy and doing it more cleverly rather than using more energy and doing it more crudely. There is a result in thermodynamics called Landor's principle, after the physicist Rolf Landor, which establishes a theoretical minimum energy cost for erasing a bit of information. At room temperature, this minimum is about 3 times 10 to the negative 21 joules per bit erased. This is an extraordinarily small number. Our current computers are orders of magnitude less efficient than this theoretical limit. A sufficiently advanced computation system could, in principle, perform an enormous amount of processing per unit of energy by approaching that thermodynamic limit. And if the goal is to run the richest possible conscious experience on the smallest possible energy budget, the direction of development points toward quiet, efficient, invisible computation rather than loud, wasteful, detectable energy consumption. A civilization a billion years old, if it has gone down this path, might be running an inner life of staggering richness and complexity on an energy budget that looks, from the outside, like a quiet star in an unremarkable planetary system. It would not look like what we are searching for. It would not look like anything. It would look like background. This possibility has a name in the literature. It is sometimes called the transcension hypothesis, proposed by the futurist John Smart. The basic claim is that advanced civilizations do not expand outward into space. They expand inward into inner space, into the miniaturization and densification of their computational and physical processes, towards smaller scales, higher efficiencies, lower energy signatures, greater inner complexity. Rather than spreading across the galaxy in ways that are obvious from the outside, they collapse toward a point of maximum computational density, becoming more and more invisible to external observers as they become more and more internally rich. If this is correct, then the silence of the cosmos is not evidence of absence. It is evidence of success. Every civilization that has survived long enough has gone through the same transition, from an expansive, energy-hungry, radio-leaking young civilization to a quiet, efficient, inward-facing old one. And the old ones are invisible not because they are hiding, but because efficiency and miniaturization are what technology looks like when it has had enough time to mature. There is another version of invisibility that deserves its own careful examination, and it has to do not with the efficiency of energy use, but with the nature of the environment an old civilization might choose to inhabit. We live in what physicists call the classical world. Objects have definite positions and velocities. Events happen in definite sequences. The physics of our everyday experience is the physics of large objects behaving according to the laws that Newton and Einstein described. But underneath that classical world is a quantum world that operates by completely different rules, rules where particles exist in superpositions of multiple states simultaneously, where measurement changes what is measured, where entanglement connects distant objects in ways that have no classical analog. We have been aware of quantum mechanics for about 100 years. We are in the very early stages of learning to engineer with it, building the first generation of quantum computers and quantum communication systems. A civilization a billion years ahead of us in quantum engineering would have access to capabilities we currently cannot describe because we lack the theoretical framework to describe them. Quantum computation at scale allows the simulation of physical systems of arbitrary complexity with an efficiency that has no classical equivalent. A sufficiently advanced quantum computer could, in principle, simulate an entire universe at the level of physical detail we experience as real. The physicist David Deutsch has argued that the laws of physics permit the construction of computers powerful enough to simulate any physically possible environment with arbitrary fidelity. If that is true, then a civilization that has mastered quantum computation at a sufficiently large scale has access to an unlimited supply of simulated realities, each one indistinguishable from the physical universe to the minds experiencing it. What would such a civilization look like from the outside? It would look like a very small physical footprint running a very large amount of computation. It would have no reason to build megastructures across the galaxy. It would have no reason to colonize other star systems. It would have no reason to communicate with the outside universe in ways detectable by less advanced civilizations, because everything it could want to experience or explore could be provided internally. It would be quiet, small, and undetectable by the methods we currently use. None of this is certain. These are theoretical possibilities, not confirmed realities, but they are possibilities grounded in physics we already know, extended along trajectories that follow from principles we already accept. And the reason they matter is that they change the framing of the Fermi Paradox in a fundamental way. The Fermi Paradox assumes that an old civilization would be detectable, that oldness and visibility go together, that a billion-year-old civilization would have left obvious marks across the galaxy that we would be unable to miss. The transcension hypothesis and related ideas suggest the opposite, that oldness and invisibility go together, that the natural trajectory of intelligence is towards smaller, quieter, more efficient, more internal ways of being, and that what we would expect to find if old civilizations exist is exactly what we do find: silence. A cosmos that looks uninhabited to a young civilization that does not yet know how to read the signs of an older one. The question then becomes, are there signs? Are there things in the universe that would look like background to us but might be, if we knew what we were looking for, the signatures of civilizations that have long since stopped looking anything like us? This is not a question with a clean answer. But there are places where physicists and astronomers have identified things that are anomalous, things that natural processes do not straightforwardly explain, things that sit at the edge of our current understanding in ways that keep careful thinkers from being entirely comfortable dismissing them. The first category is anomalous stars. We already mentioned Tabby's star. It is not the only star with unusual behavior that has attracted attention in the context of the search for extraterrestrial intelligence. There is a class of objects called anomalously dim white dwarfs that are cooler and dimmer than they should be given their estimated ages, as if something is removing energy from them at a rate inconsistent with simple cooling. There are stars with infrared excesses that do not match any known natural circumstellar dust configuration. There are stars whose light curves show periodic variations that do not match any known type of stellar oscillation or orbital transit. Most of these anomalies have natural explanations that are more plausible than artificial ones. But not all of them have been fully explained, and the standard scientific response to an unexplained anomaly is not to assume the most dramatic explanation, but to keep looking until a satisfying one is found. In some cases, that satisfying explanation has not yet arrived. The second category is anomalous signals. In addition to the WOW signal, there have been other radio detections over the decades of SETI research that produced brief excitement before being explained away or simply fading without repetition. More recently, the discovery of fast radio bursts, millisecond duration pulses of radio emission from cosmological distances, generated significant discussion about their possible origin. When they were first discovered in 2007, their origin was completely unknown, and their energy output seemed to require an extraordinary physical mechanism. Since then, at least some fast radio bursts have been traced to magnetars, highly magnetized neutron stars capable of producing enormous bursts of radiation. But the category remains diverse, and not all fast radio bursts fit neatly into the magnetar model. Some researchers have noted that certain properties of fast radio bursts, their dispersion, their repetition patterns, their energy budgets, are consistent with what you would expect from a very powerful transmitter at cosmological distances, not inconsistent with natural explanations, but not inconsistent with artificial ones either. The honest position is that fast radio bursts are not explained by a single clean mechanism, and the full picture of what produces them remains an active area of research. The third category is anomalous structures. The large-scale structure of the universe, as we discussed in detail earlier tonight, follows from the physics of gravitational instability acting on the initial density fluctuations of the Big Bang. The cosmic web that results is well described by simulations based on known physics, but there are features of the large-scale structure that are slightly harder to explain than others. The axis of evil in the cosmic microwave background, the slight preferred direction in the largest-scale temperature fluctuations, is one. The cold spot in the CMB, a region of anomalously low temperature that some researchers have associated with an enormous void, and others have suggested might be a signature of something more exotic, is another. None of these anomalies has a confirmed artificial explanation, but they are anomalies, and anomalies are where interesting physics tends to hide. What all of this points toward is not a conclusion but a posture. The posture of taking seriously the possibility that we are looking for the wrong things in the wrong ways, that the universe may be far more inhabited than it appears to our current instruments and frameworks, and that the silence we observe may be the silence of civilizations that have outgrown the phase of existence in which they would look like anything we would recognize as a civilization. There is a thought experiment that brings this into focus. Imagine you are an ant living in the walls of a large house. The house is full of humans going about their lives. There are conversations happening, music playing, food being prepared, children running, complex social dynamics unfolding. From your perspective inside the wall, none of this is visible. You can detect temperature gradients. You can sense vibrations. You can find food crumbs that the humans leave behind. But you have no framework for understanding that the temperature gradient you feel is a thermostat being adjusted, that the vibrations are footsteps, that the food crumbs are the byproduct of an elaborate meal being prepared according to a recipe that took years to develop. The house is full. It is busy. It is inhabited by minds enormously more complex than your own, and from inside the wall, it appears to be an environment with interesting physical gradients and occasional unexplained food sources. We may be the ant. The universe may be the house. The question is not whether something is there. The question is whether we have yet developed any faculty for perceiving it correctly. This does not mean that every anomaly is artificial, or that the silence of the cosmos is definitely explained by invisible ancient civilizations, or that we should abandon the search for obvious radio signals in favor of looking for things we cannot yet define. It means that the search should be broader than it currently is, that the assumptions baked into our current search strategies deserve examination, and that the possibility of civilizations old enough to be invisible is not a fringe idea, but a serious implication of the timescales involved. The universe has been old enough for a billion-year civilization to exist for a very long time. The conditions for rocky planets and liquid water have existed in parts of the galaxy for 6 to 8 billion years. If life arises anywhere given the right conditions, and if intelligence is a natural trajectory of complex life, and if a small fraction of intelligent civilizations survive their technological adolescence and continue developing for billions of years, then there is enough time in the history of the galaxy for civilizations to have reached ages and capabilities that we do not yet have the physics to fully describe. The question of what they look like from the outside is not settled. The question of whether they are there at all is not settled. But the question of whether they could exist and be invisible to us has an answer, and the answer is yes. And the reasons why are grounded in physics and engineering logic that gets more compelling the longer you sit with it. What we know for certain is that we are young. 100 years of radio technology, 400 years of formal science, 10,000 years of recorded knowledge. Against a universe that is 13.8 billion years old, we have barely opened our eyes. The question of what has been happening out there while we were still learning to look is one of the most important questions we have ever asked, and we have not yet developed the tools to answer it, but we are developing them. And the shape of the answer, when it comes, may be nothing like what we currently expect. Tonight we have been thinking about what it means for a civilization to be old, what it means to have had a billion years to develop and change, and possibly transform into something that does not resemble its starting point in any way we would recognize. The trajectory from where we are to that endpoint is impossible to trace in detail, because the details depend on choices and discoveries that have not been made yet. But the starting point is clear, and the timescales are clear, and the physics is clear. And when you put those three things together, the picture that emerges is not a universe that is silent because it is empty. It is a universe that may be full of things that have simply learned to be quiet in ways we are only beginning to suspect. The ant-in-the-wall thought experiment is useful, but it has a limitation. Ants and humans are both biological creatures living in the same physical world, breathing the same air, subject to the same chemistry. The ant cannot understand what the human is doing, but if it could, it would recognize the human as alive, as something that moves and produces heat and leaves chemical traces. The gap between them is cognitive, not ontological. They share a substrate. But a civilization that has been developing for 1 billion years may not share our substrate in any meaningful sense. It may have moved so far from the conditions of its biological origin that the word civilization, with all the images it carries of cities and tools and communication, no longer applies to what it has become. What it has become may be something for which we do not yet have a word, something that interacts with the physical universe at levels, and in ways that our current physics can barely gesture toward. This is not mysticism. It is a straightforward extrapolation from physics we already know, applied to timescales that are available in the history of the galaxy. To see why, consider what the directions of our own technology are already pointing toward, and then consider what those directions look like when you extend them not by decades or centuries, but by millions and billions of years. We are currently learning to manipulate matter at the atomic scale. Nanotechnology in the broadest sense, the ability to arrange atoms into specific configurations to achieve desired properties and functions, is in its infancy but developing rapidly. The first generation of nanoscale machines already exists in biology. Ribosomes are molecular machines that read genetic code and assemble proteins from amino acids with extraordinary precision, at scales of a few nanometers, running continuously in every living cell. We did not design ribosomes. Evolution did. But we are beginning to design our own nanoscale machines, and the trajectory of that work points toward an ability to engineer matter from the bottom up, atom by atom, into any structure permitted by chemistry and physics. A civilization that has been developing nanotechnology for 1 million years would have capabilities in this area that are, relative to our current position, roughly what our current position is relative to a chimp using a stick to extract termites from a mound. The chimp is doing tool use. We are doing molecular engineering. A 1 million-year civilization is doing something that we cannot yet name. At the scale below atoms, there is nuclear and subnuclear physics. We have learned to release energy from atomic nuclei, both through fission and fusion. We have built particle accelerators that probe the structure of matter at the level of quarks and gluons. We have developed a theoretical framework, the Standard Model of particle physics, that describes the fundamental building blocks of matter and their interactions with extraordinary precision. But there is physics below the Standard Model that we know exists and do not yet understand. The unification of quantum mechanics and general relativity, the theory of quantum gravity, is one of the central unsolved problems of physics. String theory, loop quantum gravity, and other approaches have made progress, but none has produced confirmed experimental predictions at a level that constitutes resolution. A civilization that has solved quantum gravity and spent 1 million years engineering with it has access to the structure of spacetime itself as a medium for technology. What you can build when you can engineer spacetime is something we cannot currently describe because we do not yet have the theory. There is a concept in physics called exotic matter, material with properties that are not found in ordinary matter as we know it. Negative energy density is one such property. theoretically permitted by quantum field theory in certain configurations. Negative energy density is required for the construction of stable wormholes, the kind of shortcut through spacetime that appears in the mathematics of general relativity. It is also required for the Alcubierre drive, a theoretical propulsion system that would allow faster-than-light travel by contracting space in front of a vessel and expanding it behind, without the vessel itself exceeding the local speed of light. Both of these require amounts of exotic matter that are, by current estimates, either impossible or require engineering at scales we cannot currently approach. But current estimates are based on current physics and current engineering. A civilization with 1 billion years of development in quantum gravity and material science may have a relationship with exotic matter that is no more exotic to them than semiconductors are to us. This is speculative in the specific sense that we cannot calculate it from first principles because we do not have the first principles. But it is not arbitrary speculation. It follows the logic of the history of physics, which is a history of capabilities that seemed permanently impossible becoming routine as the underlying theory was developed and the engineering matured. Flight was permanently impossible until it was not. Atomic energy was science fiction until it was physics. The manipulation of individual atoms was unimaginable until it was a laboratory demonstration. Quantum computers that solve problems intractable to classical machines were theoretical curiosities until they were devices you could access through a cloud service. The history of what seemed impossible and then became possible is a guide to humility about what we currently classify as permanently beyond reach. A civilization 1 billion years old has had time to encounter and solve every problem that sits between our current physics and whatever the final theory of everything turns out to be. It has had time to move through the phase where quantum gravity was unsolved, the phase where exotic matter was theoretical, the phase where engineering at the Planck scale was impossible, and out the other side into capabilities that we cannot currently describe. What it has built with those capabilities may look, from the outside, like nothing at all, or it may look like the universe itself, arranged in ways that we read as natural because we do not yet know what arranged looks like at that level. This brings us to one of the most unsettling possibilities in the entire discussion of ancient civilizations, and it is one that physicists take more seriously than popular science coverage usually acknowledges. It is the possibility that dark matter is not a natural substance, but an engineered one. Or more precisely, that some fraction of what we call dark matter is the material residue of civilizations that have moved their existence off the ordinary matter platform entirely. Dark matter, as we discussed earlier in this series, is real. Its gravitational effects are measured and confirmed across many independent lines of observation. It constitutes approximately 27% of the total energy content of the universe and accounts for the dominant mass component of every galaxy and galaxy cluster we have studied. But what it is made of remains one of the deepest unsolved problems in physics. Decades of searches for WIMP particles, the leading candidate, have returned nothing. Axion searches continue without confirmed detection. The identity of dark matter remains genuinely open. The physicist Caleb Scharf, in a paper that caused significant discussion when it was published, raised the possibility that at least some portion of what we observe as dark matter could be the product of life and intelligence rather than a primordial physical substance. The argument is not that all dark matter is artificial. It is that we have no confirmed explanation for what dark matter is, that the universe is old enough for civilizations to have had billions of years of development, and that a sufficiently advanced civilization might choose to migrate its existence into a substrate that interacts with ordinary matter only gravitationally, which is exactly what dark matter does. Such a civilization would be, from our perspective, indistinguishable from a natural dark matter component. Its gravitational effects would be present and measurable. Its direct interactions with our instruments would be zero. It would be, in the most complete possible sense, invisible. This is not a claim that dark matter is aliens. It is a claim that the possibility cannot currently be ruled out, that it is consistent with known physics, and that taking it seriously changes the question from why is the universe silent to how would we even know if it were not. A civilization that has reorganized its physical substrate to interact with ordinary matter only through gravity has made itself permanently undetectable to any instrument that relies on electromagnetic interaction, which is every instrument we currently have. It is not hiding. It is simply living in a different layer of the physical world, one that intersects with ours only through the weakest and most diffuse of the fundamental forces. There is another direction that does not require exotic physics, but is equally difficult to detect, and it has to do with the interior of stars. Stars are usually thought of as hostile environments, places where temperatures reach millions of degrees, and the radiation environment would destroy any known material in moments. But this is the perspective of biology that evolved on a cool, rocky planet. From a physics standpoint, a star is an energy-rich environment with a stable power source that will last for billions of years, a strong magnetic field, complex plasma dynamics, and a wide range of physical conditions from the relatively cool surface to the extremely hot core. A civilization that has moved beyond biological substrate and beyond the need for mild temperatures and solid surfaces might find a stellar interior not hostile, but simply a different kind of physical environment, one with certain engineering challenges and certain advantages. The physicist Freeman Dyson, who proposed the Dyson sphere, also speculated about what he called stellivores, civilizations that live inside stars rather than around them, feeding on the stellar plasma and the energy it contains. This is not as absurd as it first sounds. The interior of a star is not chaos. It has structure. The plasma convects in organized patterns. The magnetic field organizes into coherent structures that we observe at the stellar surface as sunspots and prominences. There is information in a stellar interior, and where there is information there is, in principle, the possibility of information processing. A civilization that has mastered the physics of plasma at high temperatures and the engineering of magnetic fields at stellar scales might find the interior of a star to be a perfectly adequate computational and energetic substrate. From outside, it would look like a normal star with perhaps some anomalous surface features. It would not look like a civilization. Neutron stars are even more interesting from this perspective. A neutron star is the remnant of a massive star that ended its life in a supernova, a sphere of neutronium roughly 20 kilometers in diameter, containing roughly 1.5 times the mass of our Sun. The density is incomprehensible by ordinary standards. A teaspoon of neutron star material would weigh 100 million tons on Earth. The surface gravity is 200 billion times Earth's. The magnetic field is 1 trillion times stronger than Earth's. The rotation rate of young neutron stars, called pulsars, can be hundreds of times per second. These are extreme environments by any measure we can apply, but they are also environments with enormous energy densities, stable rotation that could serve as a clock for computational processes, and physical conditions so far from anything we have experience with that our intuitions about what is possible inside them are essentially worthless. A civilization that has had 1 billion years to study and engineer neutron star physics would have access to computational and energetic resources that dwarf anything available in a planetary environment. In a package 20 kilometers across that would look, from a distance, exactly like a normal neutron star. The physicist Robert Forward explored the theoretical possibility of life forms based on nuclear rather than chemical interactions, creatures built from nuclear matter, whose biochemical reactions are nuclear rather than electromagnetic. Such organisms would be microscopic by our standards, living on timescales millions of times faster than us, experiencing entire evolutionary epochs in the time it takes us to blink. Forward's work was theoretical and speculative, but it was grounded in the physics of nuclear interactions, and served as an existence proof that life as we know it, carbon-based and electromagnetic, is not the only physical configuration that could sustain self-organizing complexity. A neutron star harboring nuclear life would look, from outside, exactly like a neutron star. Its inhabitants would be as unaware of us as we are of them, living in a physical regime so different from ours that the possibility of communication, let alone recognition, is essentially nil. None of these possibilities, dark matter civilizations, stellar civilizations, neutron star civilizations, are confirmed, but they illustrate a point that is important for understanding the scale of our ignorance about what the universe might contain. We search for life and civilization using the assumptions of our own existence. We look for carbon chemistry, liquid water, mild temperatures, electromagnetic communication, visible light or radio wave signatures. These assumptions are reasonable given that we are the only example of life we have, but they are not physically motivated in the sense that the laws of physics do not restrict life and intelligence to these particular substrates. They are motivated by familiarity. We look for things like us because things like us are the only things we know how to look for. A billion-year-old civilization almost certainly does not look like us in any meaningful sense, even if it started as something biologically similar to us. A billion years is enough time for a species to change beyond recognition, even under biological evolution alone, without any technological intervention. Add a billion years of technological development, and the original biological form becomes a historical curiosity. The way the first self-replicating molecules are a historical curiosity to us now. What a civilization looks like after a billion years of development is determined by the physics of its universe and the choices it made along the way, not by the biology of its ancestors. This raises a question that is less often asked but equally important. Would a billion-year-old civilization want to be detected? The assumption built into most SETI work is that advanced civilizations would either actively try to communicate with younger ones or would be indifferent to whether they were detected. But there is a third possibility. A civilization that has thought carefully about the dynamics of civilizations in the galaxy might have concluded that broadcasting your existence is not necessarily wise. This is the dark forest hypothesis, articulated by the Chinese science fiction writer Liu Cixin, and named for the idea that the universe is like a dark forest in which every hunter must move silently, because every other hunter is also armed, and the consequences of being heard are unpredictable. The dark forest logic goes like this. Resources in the universe are finite. Any civilization that expands far enough will eventually face resource constraints. A civilization that encounters another civilization cannot know in advance whether that other civilization poses a threat to its resources or its existence. The cost of being wrong about a benign civilization is low. The cost of being wrong about a hostile one is extinction. Given that asymmetry, a rational civilization might conclude that the safest policy is to eliminate any other civilization it becomes aware of, before that civilization has the chance to develop to a level where it poses a threat. And if every sufficiently advanced civilization reaches this conclusion, then the galaxy becomes a place where silence is the only safe strategy. Every civilization that announces itself risks being targeted by others. Every civilization that has survived long enough to become powerful enough to be a threat has learned to be quiet. Liu Cixin's formulation is a piece of science fiction reasoning rather than a scientific argument, but it has been taken seriously by physicists and scholars of the Fermi Paradox because its logic is internally consistent and its implications are genuinely disturbing. If the dark forest hypothesis is correct, then the search for extraterrestrial intelligence is not just unlikely to succeed because civilizations are rare or invisible. It is actively dangerous because the civilizations that are old enough and powerful enough to have survived are the ones that learn to hide, and any civilization that announces itself to the galaxy is marking itself as a target. the physicist Stephen Hawking warned publicly on multiple occasions against the deliberate broadcasting of signals intended to attract the attention of extraterrestrial civilizations. His reasoning was not precisely the dark forest model, but was similar in spirit. We do not know what is out there. We cannot know in advance whether contact would be benign or catastrophic, and the asymmetry between what we might gain and what we might lose argues for caution. This is a minority view in the SETI community, where the prevailing attitude is that the universe is too large and communication too slow for contact to pose an immediate danger, and where the potential benefits of learning from a more advanced civilization are considered worth the theoretical risk. But the disagreement is real, and the argument for caution is not frivolous. There is a version of the dark forest hypothesis that does not require malice. Even a benign civilization might choose not to broadcast its existence simply because contact between civilizations at very different levels of development has historically on Earth been damaging to the less developed one. Every encounter in human history between a technologically superior civilization and a less developed one has resulted in disruption, cultural erosion, or destruction of the less developed culture. This is not inevitable, and it does not require the more advanced civilization to be hostile. The disruption comes from the mere presence of a more powerful and technologically capable neighbor, which changes the context in which the less developed civilization exists in ways that are often beyond its ability to manage. A genuinely benign, advanced civilization that was aware of this dynamic might choose to observe without contact, to wait until the younger civilization had developed enough to engage as something closer to an equal, or to avoid the encounter entirely on the grounds that the asymmetry makes a good outcome unlikely. This is sometimes called the zoo hypothesis in the SETI literature, the idea that Earth is being deliberately left alone by advanced civilizations that are aware of us but have chosen non-interference as their policy. It is essentially impossible to distinguish from the null hypothesis of simply no advanced civilizations being present, because in both cases the observable result is silence. But it has an interesting implication. If it is correct, the silence is not evidence of absence. It is evidence of restraint, and restraint is something a sufficiently wise civilization might choose. The SETI Institute and associated researchers have, over the decades, gradually broadened the search strategies to account for some of these possibilities. The original focus on radio signals has been supplemented by optical SETI, searching for laser pulses that might carry information. There are now searches for anomalous stellar behavior that might indicate engineering. There are searches for technosignatures in the spectra of planetary atmospheres, chemical compositions that would be inconsistent with purely natural chemistry. There are proposals for searching for evidence of large-scale engineering in the distribution of matter in the galaxy, patterns in stellar populations that might reflect deliberate manipulation rather than natural stellar dynamics. None of these searches has produced a confirmed positive result. But the expansion of the search space reflects a growing recognition that the original assumptions of SETI were too narrow, that if we are looking for signals that look like human radio transmissions, we are probably looking for the wrong thing. The most sophisticated current thinking about technosignatures takes as its starting point not what we would produce if we were trying to be detected, but what physical processes leave signatures in the universe that cannot be produced by known natural mechanisms. This is a more demanding standard than looking for something that looks artificial. It requires looking for something that cannot be natural, which means knowing natural processes well enough to identify their limits. A galaxy with an anomalous infrared signature is interesting but not conclusive because natural dust distributions can produce infrared excesses. A star with a light curve that no known physical process can explain is more interesting, and Tabby's star sits in that category even after several years of study. A pattern in the distribution of elements or isotopes across a stellar system that violates the predictions of stellar nucleosynthesis would be even more interesting, because stellar nucleosynthesis is well understood and its predictions are precise. The physicist Milan Čerković has written extensively about what he calls the temporal dispersion of intelligence in the galaxy, the idea that civilizations do not all arise at the same time, but are spread across the full history of the Milky Way, with the earliest ones having had billions of years of development before the Sun even formed. Čerković argues that this temporal dispersion has profound implications for the Fermi Paradox and for the expected observational signatures of advanced civilization. A galaxy in which intelligence has been present for billions of years is not a galaxy full of civilizations all roughly similar to us. It is a galaxy in which some civilizations are billions of years ahead of us, and those civilizations have had time to do things whose consequences might be written into the structure of the galaxy itself. What kinds of consequences? One possibility is stellar engineering. The lifetimes of stars are determined by their mass. More massive stars live shorter lives, less massive stars live longer. Our Sun will last about 10 billion years. Red dwarf stars, the most common type in the Milky Way, can last for trillions of years. A civilization that wanted to ensure its energy supply for the longest possible time would prefer to live around a red dwarf, and a civilization with sufficient stellar engineering capability might choose to migrate its home star to a more desirable mass range, either by adding mass to a dimming star or by adjusting the mass loss rate of a large one. There is no confirmed evidence of this in the galaxy, but the stellar mass distribution of the Milky Way is not perfectly predicted by natural star formation models, and the discrepancies are generally attributed to incomplete understanding of star formation physics rather than to artificial intervention. Which is the right interpretation of those discrepancies is a question that the data does not currently resolve. Another possibility is the engineering of planetary systems. A civilization with sufficient capability might want to move planets to more desirable orbits, to redirect cometary bodies to deliver water to dry planets, to terraform hostile worlds into habitable ones, to adjust the rotation rates or axial tilts of planets to produce more stable climates. All of these are things that are physically possible in principle, and that a sufficiently advanced civilization could achieve. From the outside, the result would look like a planetary system with an unusually favorable configuration, which we might attribute to good luck in the natural formation process. The line between a naturally fortuitous planetary system and a deliberately engineered one is not observable from our current position, because we do not have a complete enough understanding of natural planetary formation to know what a random draw from that distribution looks like. There is also the possibility of deliberate panspermia, the seeding of life across the galaxy by a civilization that has decided to spread biology as broadly as possible. The idea that life might travel between star systems on meteorites or other debris is called natural panspermia and is a legitimate scientific hypothesis for how life might have been distributed in the early solar system. Directed panspermia, the deliberate seeding of other worlds with life by an intelligent civilization, was proposed seriously by Francis Crick, the co-discoverer of DNA, and the biochemist Leslie Orgel in 1973. Crick and Orgel pointed to certain features of the genetic code that seemed to suggest a common origin for all life on Earth at a time when natural abiogenesis seemed difficult to account for, and suggested that the simplest explanation might be that life on Earth was deliberately introduced from elsewhere. This hypothesis has not been confirmed, and the subsequent development of abiogenesis research has produced more plausible natural explanations for the origin of the genetic code. But the underlying logic of directed panspermia remains interesting regardless of whether it applies to Earth specifically. A civilization that discovered biology as a fundamental property of the universe, that understood the conditions under which life arises, and the timescales required for it to develop intelligence, and that wanted to ensure the widest possible distribution of intelligence across the galaxy might choose to seed habitable worlds with the basic biological machinery needed to start the process. The investment is small, a probe carrying genetic material or self-replicating chemistry to a suitable planet. The payoff, if the life develops into intelligence over the following billions of years, is enormous, and the signature of this intervention from our perspective billions of years later would be invisible. Life would simply appear to have arisen naturally on Earth, because the seeding event happened so long ago, and the subsequent biological evolution was entirely natural. We would have no way to distinguish seeded life from spontaneously generated life, without an extraordinarily detailed understanding of the precise biochemical pathway from chemistry to the first self-replicating molecules, and that understanding does not currently exist. The implication is disquieting in a specific way. If directed panspermia has occurred in the galaxy, and if the civilization that performed it is still extant and monitoring its results, then we may already be known. We may have been observed for the entire duration of our existence as a species. The silence we interpret as the absence of other intelligence may be the silence of an observer that seeded us and is watching to see what develops, choosing non-interference for reasons we cannot know from our current position. This is not a comfortable thought, but comfort is not a criterion for taking a hypothesis seriously. The criterion is whether it is consistent with the physics and with the observations, and the directed panspermia hypothesis, in its broad form, satisfies both. All of these possibilities, dark matter civilizations, stellar and neutron star civilizations, civilizations that have chosen the transcension path, civilizations practicing deliberate silence for strategic or ethical reasons, civilizations that seeded us and are watching, share a common feature. They are all consistent with a universe that appears, to our current instruments and frameworks, to be silent and uninhabited. They do not require the universe to be different from how we observe it. They require us to be different from how we currently are, more sophisticated in our search strategies, more humble about our assumptions, more willing to consider that the thing we are looking for may not look like anything we expected. The physicist Paul Davies, in his book The Eerie Silence, makes this point forcefully. He argues that SETI as currently practiced is looking for the right thing in approximately the wrong way, and that a serious engagement with the question of what old civilizations look like requires a fundamental rethinking of the search, not abandoning it, but expanding and reorienting it, looking not just for signals that look like ours, but for physical anomalies that cannot be explained by natural processes. Looking not just in the radio spectrum, but across the full range of physical signatures. Looking not just for civilizations that are trying to be detected, but for the physical residue of civilizations that are not. Davies also makes a point that is easy to miss in the standard Fermi Paradox discussion. The absence of evidence is not evidence of absence, but the strength of that argument depends on how hard you have looked. We have been looking, in a serious and systematic way, for about 60 years. We have surveyed a relatively small fraction of the sky in a relatively narrow frequency range, with instruments of limited sensitivity, by the standards of what a more advanced civilization would be able to produce. The conclusion that the universe is silent because 60 years of radio searching has found nothing is approximately as well-founded as the conclusion that there are no fish in the ocean because you dropped a fishing line in one spot for an hour and nothing bit. The absence of a signal in our current searches is a weak constraint on the prevalence of intelligence in the universe. It rules out certain specific possibilities, powerful deliberate transmitters aimed at us in certain frequency ranges, but it is consistent with essentially every other scenario. This is not a reason for complacency. It is a reason for ambition. The question of whether we are alone, or whether the universe is populated with civilizations, some of which are incomprehensibly older than us, is one of the most important questions we could possibly ask, and one of the most consequential we could possibly answer. The resources devoted to answering it, across all of the relevant research programs, are tiny compared to the importance of the question. The Breakthrough Listen initiative, funded by the Russian billionaire Yuri Milner at $100 million over 10 years beginning in 2015, is the largest private investment in SETI in history and the most comprehensive search program ever undertaken. It is also, in the context of global research spending, a very modest investment in what may be the most significant scientific question there is. The next generation of telescopes and surveys currently under construction or in development will dramatically expand the search space. The Square Kilometre Array, a radio telescope distributed across South Africa and Australia, whose total collecting area will be roughly a square kilometer, will be sensitive enough to detect radar emissions equivalent to our own military radar from a distance of several light years, for the first time giving us a realistic chance of detecting the kind of leakage radiation that Earth currently produces from nearby star systems. The James Webb Space Telescope, already in operation, is providing atmospheric spectra of exoplanets with a sensitivity that will allow detection of chemical disequilibria that might indicate biology. The Vera Rubin Observatory is conducting an all-sky survey that will identify transient events and anomalous stellar behavior at a rate orders of magnitude beyond previous surveys. The next 2 decades of observational astronomy will produce a flood of data about the universe at a level of detail that has never been available before. Whether any of that data will contain a signal or an anomaly that cannot be explained by natural processes remains to be seen. The honest answer is that we do not know. We do not know if old civilizations exist. We do not know if they are invisible. We do not know if the silence we currently observe is meaningful or simply the result of looking in the wrong place in the wrong way. What we know is that the universe is old enough for civilizations of incomprehensible age to exist, that the physics of technology points in directions that lead to invisibility rather than prominence, and that the search we have conducted so far is nowhere near comprehensive enough to justify strong conclusions about whether we are alone. What we also know, and this is worth sitting with for a moment before we continue, is what it would mean if the invisible civilizations hypothesis is correct. If the universe is populated with old intelligences that have moved beyond the phase of existence in which they would look like anything we recognize, then the cosmos is not the empty, silent place it currently appears to be. It is a place full of minds, full of experience, full of histories that dwarf ours in every dimension, existing in physical substrates we cannot currently detect, in timescales that make our entire civilizational history look like a single heartbeat. The loneliness we feel when we look up at the night sky and find no obvious company is a loneliness born of youth and limited perception, not a loneliness that reflects the actual state of the universe. And if that is true, then the universe we inhabit is not the universe it appears to be. The silence is not silence. It is a conversation happening at a level we cannot yet hear, in a language we have not yet learned, between minds that have had billions of years to develop ways of being that we cannot yet imagine. We are the newest voices in a very old conversation, just beginning to understand that speaking is possible, not yet aware of who else is in the room. The question of whether we will ever be able to hear them, whether the gap between our current instruments and the instruments needed to detect an invisible civilization is closable in principle or simply too large to cross, is something we will spend time with next. Because even if the invisible civilizations exist, even if the universe is full of old minds living in dark matter or stellar interiors or quantum computational substrates, the question of whether we could ever know it is separate from the question of whether it is true. And that question has an answer that is not entirely discouraging, for reasons that have to do with the physics of what information old civilizations might have left behind, and where we might find it if we know how to look. The question of whether we could ever detect an invisible civilization is not the same as the question of whether invisible civilizations exist. They are separate questions, and they have separate answers. The first is a question about our instruments and our ingenuity. The second is a question about the universe, but they are connected in a specific way that matters for how we think about the search. If detection is in principle impossible, then the question of existence becomes permanently unanswerable, and we are left with a philosophical problem rather than a scientific one. If detection is in principle possible, even if it requires instruments and methods far beyond what we currently have, then the question remains scientific, and the work of closing the gap between where we are and where we need to be becomes one of the most important research programs in history. The encouraging news is that detection, even of civilizations that have gone to considerable lengths to minimize their observable footprint, may not be permanently impossible. The reason has to do with a principle that is built into the laws of physics at a very deep level, and that no amount of engineering sophistication can overcome. The principle is this: information cannot be created or destroyed, and every physical process leaves a record, not always a readable record, not always a recoverable one, but a record nonetheless, written into the state of the physical universe in a way that the laws of quantum mechanics say cannot be entirely erased. This principle, sometimes called the conservation of quantum information, is one of the things that Stephen Hawking spent the last decades of his life arguing about with other physicists. His original formulation of black hole thermodynamics suggested that black holes destroy information, that matter falling into a black hole loses its quantum state permanently when the black hole eventually evaporates. Most physicists came to believe that this could not be correct, that the information must somehow be preserved in the Hawking radiation that the black hole emits as it evaporates, even if the way it is encoded in that radiation is so scrambled as to be practically unrecoverable. The consensus today, though not unanimous, is that information is conserved. The universe keeps records. The question is only whether we can read them. Every civilization that has ever existed, regardless of what it subsequently became, left physical traces in the universe at the time of its existence and through its subsequent development. A civilization that burned fossil fuels changed the isotopic composition of its planet's atmosphere. A civilization that built nuclear reactors produced isotopes that do not occur naturally in significant quantities. A civilization that conducted nuclear weapons tests scattered specific fission products across its planet and into space. A civilization that built particle accelerators produced exotic particles that then decayed into daughter products that would not otherwise be present in those concentrations. These are the traces of a young civilization, a civilization in the equivalent of our current phase. They are small and local and would be essentially undetectable from another star system with current technology, but they are there. As a civilization advances, the scale of its physical interventions presumably grows. A civilization that has colonized its solar system has rearranged matter at a solar system scale. A civilization that has built Dyson structures has altered the infrared signature of its star. A civilization that has engineered its stellar neighbors has changed the mass distribution and lifetime distribution of stars in its region of the galaxy. A civilization that has conducted stellar engineering on a galactic scale has left changes in the stellar population that might persist for billions of years after the civilization itself has moved on to whatever it became next. These large-scale traces are what cosmologists and SETI researchers mean when they talk about astroengineering signatures, the physical marks left on the galaxy by civilizations that were large and active enough to rearrange its contents. The argument for looking for them is that they are persistent. A star moved to a different orbit or adjusted to a different mass stays in that configuration long after the civilization that moved it has gone silent or transformed. The galaxy, if it has been inhabited by technological civilizations for billions of years, may carry in its current stellar distribution the accumulated record of billions of years of astroengineering. We would not necessarily recognize it as such, because we do not have a detailed enough model of what the galaxy's stellar distribution should look like under purely natural processes to identify the deviations with confidence. But as our models of stellar formation and galactic dynamics improve, the deviations may become identifiable. There is a specific category of astrophysical object that deserves particular attention in this context, and it is one that has attracted increasing interest in recent years for reasons that have nothing to do with the search for extraterrestrial intelligence, but that may turn out to be relevant to it. The category is anomalous isotope ratios in stellar spectra and in the interstellar medium. Stars and the gas clouds from which they form have isotopic composition that are predicted with considerable precision by the theory of stellar nucleosynthesis. Each generation of stars produces specific ratios of specific isotopes, which are then scattered into the interstellar medium by stellar winds and supernovae, enriching the gas that forms the next generation. The isotopic composition of our own solar system, as measured in meteorites and in the solar spectrum, is broadly consistent with this picture, the product of several generations of stellar nucleosynthesis before the Sun formed. But there are anomalies. Certain meteorites contain isotopic signatures that require a specific type of stellar event, a nearby supernova or the wind from an asymptotic giant branch star, to have occurred in the immediate vicinity of the forming solar system within the last few million years before the Sun's formation. These are interpreted as natural, if somewhat fortunate, events in the Sun's birth environment, and they probably are natural. But the existence of such anomalies and our developing ability to read isotopic records in stellar spectra and in the composition of stellar remnants points toward a future capability to detect isotopic compositions that are inconsistent with any natural nucleosynthesis pathway. If a civilization has conducted nuclear engineering at a large enough scale, perhaps running artificial fusion reactions with unusual fuel compositions, or producing specific isotopes for technological purposes, the residue of those reactions could persist in the interstellar medium for billions of years, and could in principle be identified by future instruments sensitive enough to read isotopic ratios in the spectra of gas clouds and stellar photospheres. Pulsar timing is another avenue that has received attention. Pulsars are rapidly rotating neutron stars whose beams of radio emission sweep past Earth at extraordinarily regular intervals, so regular that they rival atomic clocks in their stability. A pulsar timing array, a network of pulsars whose timing signals are monitored simultaneously, can detect distortions in the fabric of spacetime that pass through the array, altering the arrival times of pulses from different pulsars in correlated ways. This technique is currently being used to search for gravitational waves from supermassive black hole binaries, and recent years have produced tantalizing hints of a gravitational wave background that is now being characterized in detail. But pulsar timing arrays are also, in principle, sensitive to any large-scale distortion of spacetime, including, theoretically, the spacetime distortions that would be produced by the operation of warp drives or wormholes, if such things are physically realizable, and if a civilization somewhere were operating them at sufficient scale. The sensitivity of current pulsar timing arrays is not sufficient to detect engineering at the scales that would be relevant. Future arrays with more pulsars and longer baselines might approach the sensitivity needed. It is a long shot, but it is a shot grounded in real physics and real instrumentation. The cosmic microwave background itself may carry information about events that happened before the Big Bang, as Penrose's conformal cyclic cosmology suggests, but it may also carry information about events that happened in the very early universe that were influenced by processes we do not yet understand. There are features of the CMB, the axis of evil, the cold spot, the anomalously low quadrupole, that remain unexplained by the standard model of cosmology. Most cosmologists attribute these to statistical fluctuations, rare but possible outcomes of a random process. But a minority view holds that they might reflect real physical structure at scales comparable to the observable universe, structure that could in principle have been imprinted by processes operating at cosmic scales. Whether any such process could be the work of intelligence operating at truly cosmic scales is a question that sits at the boundary between physics and speculation. But the boundary is worth sitting at for a moment, because the question of what a type III civilization, a civilization using the energy of an entire galaxy, might leave in the structure of the cosmic microwave background is one that has not been carefully worked out and might reward serious attention. The honest summary of all of this is that we have theoretical reasons to believe that old civilizations leave physical traces, that those traces might be detectable with future instruments, and that we have not yet developed either the instruments or the search strategies that would be required to find them. We are in the position of someone who has been told that a library exists and has been given a pair of binoculars and told to find it, when what is needed is a map and a door key. The library may be there. The binoculars are not the right tool. We are working on better tools. While we work on those tools, it is worth spending some time with the question that the existence of potentially invisible civilizations raises about our own future. Because the scenario we have been describing, civilizations that grow old enough to become invisible, is not just a description of other civilizations somewhere else in the galaxy. It is a description of a possible trajectory for us. If the physics and the logic hold, then the path from where we are to whatever an invisible civilization looks like is a path that we might walk. Not soon, not in any time frame that is relevant to anyone alive today or alive in the next 10,000 years, but on the timescale of the galaxy, on the timescale that we have been thinking in tonight, the question of what we might become is not purely hypothetical. We are currently in the earliest phase of what might be a very long story, 100 years of radio technology, the first tentative steps towards space travel, the first generation of artificial intelligence, the first instruments sensitive enough to find other planets and begin characterizing their atmospheres. We are an infant civilization by any cosmic measure, and we are in a phase that is probably among the most dangerous ones on the trajectory, where our technological capability has outrun our wisdom in specific ways, where the tools we have built can destroy us before we have had time to learn how to use them well. The question of whether we survive this phase is separate from the question of what we might become if we do. But the two questions are connected, because what we might become is only available as a destination if we make it through the current passage. The civilizations that have become invisible, if they exist, made it through. They survived whatever the equivalent of our current crises was for them. They solved the problems of their technological adolescence, or at least enough of them to persist and continue developing. They found a way to be a civilization for long enough to become something else. The silence we hear from them, if the silence is theirs, is the silence of success. It is the sound of 1 billion years of making it work. That framing changes the texture of the Fermi Paradox silence in a way that is worth noting. The standard emotional register of the Fermi Paradox is unease, the unease of looking up at a universe that should be full of voices and hearing nothing, of wondering whether the silence means no one else made it, whether we are alone in a way that reflects some deep and terrible fact about the rarity of intelligence or the inevitability of self-destruction. That unease is real, and it has motivated serious scientific work. But there is another emotional register available. One where the silence is not the silence of absence, but the silence of maturity, where the cosmos is quiet not because it is empty, but because the things that have been here the longest have learned to be still. A universe full of billion-year-old minds that have chosen depth over breadth, efficiency over spectacle, inwardness over expansion, is a strange universe to inhabit as a young and noisy species. But it is not a lonely one. It is a universe that has been thinking for a very long time, in ways we cannot yet access, about things we cannot yet imagine. And we are at the beginning of our own participation in that process, just barely old enough to ask the questions, not yet old enough to understand what answering them would require. There is something that the astronomer and writer Carl Sagan said that stays useful here, even after all the more recent thinking that has complicated and extended it. He said that we are a way for the cosmos to know itself. He meant this in the sense that we are made of the same matter as everything else, that the atoms in our bodies were forged in stars, that the physical universe produced us through a long and improbable process of self-organization, and that in the act of looking up and asking questions we are, in a specific sense, the universe turning its attention on itself. It is a beautiful framing, and it is physically accurate as far as it goes. But if invisible civilizations exist, if the universe is populated with old minds living in dark matter halos and stellar interiors and quantum computational substrates, then Sagan's framing becomes larger than he intended. It is not just us through which the cosmos knows itself. We are one of the newest and least experienced participants in a process that has been ongoing for billions of years. The universe has been knowing itself through other minds, minds that have had immeasurably longer to look and think and ask and perhaps begin to understand for most of its history. We arrived late. We are still finding our seat. The conversation, if there is a conversation, has been going on without us for a very long time. This does not diminish us. It locates us. There is a difference between being small in a universe that is large and being small in a universe that is large and old and possibly full. The first is the standard description of our cosmic situation. The second is what we have been sitting with tonight. And the second is not worse than the first. It is stranger, and stranger in a way that is more interesting than mere smallness. When you go outside tonight, or when you look up from wherever you are at a window or a screen that is aimed at the night, what you are looking at is not an empty sky. It is a sky full of stars that have been burning for billions of years, around which planets have been forming and reforming, and occasionally producing the conditions for chemistry to organize itself into something that asks questions. It is a sky that is, according to the best physics we have, old enough to have produced minds a billion years more experienced than us. Whether those minds are there, whether they are listening, whether they have any awareness of us or interest in us, we do not know. The physics says they could be. The silence says only that they are not obvious, which is different from saying they are absent. The night sky is not a display. It is not a backdrop. It is not an empty stage on which we are the only actors. It is a record of 13.8 billion years of physical processes, some of which, by the logic we have been following tonight, produced intelligence that has had time to become something we cannot currently describe. Looking up at it is not looking at emptiness. It may be looking at a conversation you cannot yet hear, in a language you have not yet learned, between parties who have been speaking since before your world existed. That is not a comfortable thought, necessarily, but comfort is not what the night is for. The night is for sitting with things larger than the day allows. And this, the possibility of ancient, invisible minds in a universe that looks empty but may not be, is exactly the kind of thing the night is for. Thank you for spending these hours here. This is Dusk and Discovery. If this is where you want to come when the night needs filling, subscribe and come back. Sleep well.
So I hope you are still in this channel watching this video and hope you like this video too. If you have any suggestions uh, or anything you'd like to see on this channel, you can comment down below. And thank you